what are RNNs, right? Well, RNN basically stands for recurrent neural network. And we usually use this in order to deal with a sequential data. Sequential data can be something like a time series data or a textual data of any format. So why should one use RNN, right? Well, this is because there's a concept of internal memory here. RNN can remember important things about the input it has received, which allows them to be very precise in predicting what can be the next outcome. So this is the reason why they are performed or preferred on a sequential data algorithm. Okay. And some of the examples of sequential data can be something like time series, speech, text, financial data, audio, video, weather, and many more. Although RNN were the state-of-the-art algorithm for dealing with sequential data, they come up with their own drawbacks. And some of the popular drawbacks over here can be like, due to the complication or the complexity of the algorithm, the neural network is pretty slow to train. And as there are a huge amount of dimensions here, the training is very long and difficult to do. Okay. Apart from that, the most decisive feature for RNN or for the improvement in RNN is that of a vanishing gradient. What this vanishing gradient is that, when we go deeper and deeper into our neural network, the previous data is lost. This is because of a concept called as vanishing gradient. And due to this, we cannot work on a large or a longer sequence of data. Okay. To overcome this, we came up with some new or upgrades to the current recurrent neural networks or RNNs. Starting off with bidirectional recurrent neural network. You see, bidirectional recurrent neural network connect two hidden layers of opposite direction into the same output. With this form of generative deep learning, the output layer can get information from past, future states simultaneously. So as you can see here, we have two layers over here. And as they are bidirectional, what happens is when the algorithm feels that it is kind of losing its gradients or the previous data, it can go back and get the data from the past. So why do we need bidirectional recurrent neural network? Well, bidirectional recurrent neural network duplicates RNN processing chain so that the input process both forward and reverse time order, thus allowing bidirectional recurrent neural network to look into future context as well. The next one is long short-term memory. Long short-term memory, or also sometimes referred to as LSTM, is an artificial recurrent neural network architecture used in the field of deep learning. Unlike standard feed-forward neural network, LSTM has a feedback connections. It can not only process single data point, but also the entire sequence of data. So as you can see here, from what I'm trying to say is, with LSTM or long short-term memory, it has something like, we can feed a longer sequence compared to what it was with bidirectional RNN or RNNs. So why is LSTM better than RNN? We can say that when we move from RNN to LSTM, we are introducing more and more control over the sequence of the data that we can provide. Thus, LSTM gives us more control ability and thus better results. Alright, so the next type of recurrent neural network is the gated recurrent neural network, or also referred to as GRUs. You see, GRU is a type of recurrent neural network that is, in certain cases, is advantageous over long short-term memory. GRU makes use of less memory and also is faster than LSTM. But thing is, LSTMs are more accurate while using longer data sets. I'm sure by now you might have got a hint about the trend that has led to the improvement, right? So the trend over here is, the model should be capable of remembering and taking in on a longer input sequence. The game changer part for the sequential data was developed when we came up with something called as transformers. And this paper was something which is based on a concept called as attention is everything. Alright, so let's take a look at this. The paper, Attention is All You Need, introduces a novel architecture called as transformers. Like LSTM, transformers is an architecture for transforming one sequence into another while helping other two parts, that is encoders and decoders. But it differs from previously described sequence to sequence model because it does not work like GRUs. Okay, so it does not implement recurrent neural networks. Recurrent neural network until now were one of the best ways to capture the timely dependence on a sequence. However, the team presenting this paper, that is Attention is All You Need, proved that an architecture with only attention mechanism does not use RNN can improve its result in translation tasks and other NLP tasks. One of the best examples for transformers is Google's BERT. So what exactly is this transformer, right? You see here we have encoder on the top and decoder on the bottom. Both encoder and decoder are comprised of modules that can stick onto the top of each other multiple times. So what happens here is the inputs and outputs are first embedded into n-dimension space since we cannot use this directly. So we obviously have to encode our inputs, whatever we are providing here. One slight but important part of this model is the positional encoding of different words. Since we have no recurrent neural network that can remember how sequences are fed into the model, we need to somehow give every word or part of our sequence a relative position, since a sequence depends on the order of the elements. Okay, these positions are added to the embedded representation of each words. Alright, so this was the brief about transformers. So let us now move ahead and see some of the popular language models that are available in the market. Alright, so let us now start off by understanding OpenAI's GPT-3. The successor to GPT and GPT-2 is the GPT-3 and is one of the most controversial pre-trained models by OpenAI. The large-scale transformer-based language model has been trained on 175 billion parameters, which is 10 times more than any previous non-sparse language model. The model has been trained to achieve strong performance on many NLP datasets, including tasks like translation, answering questions, as well as several other tasks. Then we have Google's BERT. BERT stands for Bidirectional Encoder Representations from Transformers. It is a pre-trained NLP model which is developed by Google in 2018. With this, anyone in the world can train either their own question answering module with up to 30 minutes on a single cloud TPU, or few hours using single GPU. The company then released this showcasing the performance of 11 NLP tasks, including very competitive Stanford dataset questions. Unlike other language models, BERT has only been pre-trained on 250 million words of Wikipedia and 800 million words of book corpus, and has been successfully used as a pre-trained model in deep neural network. According to researchers, BERT has achieved 93% accuracy, which has surpassed any previous language models. Next, we have ELMO. ELMO, also known as Embedding for Language Model, is a deep contextualized word representation. The model developed by Allen NLP has been pre-trained on a huge text corpus and learned functions from bidirectional models, that is BiLM. ELMO can easily be added to their existing models, which drastically improves the features of functions across vast NLP problems, including answering questions, textual intent, and sentiment analysis.